All right, we've got Laurent up to teach us all about the Cuntz semigroup. And I think that it will be a bit shorter today because he has to run off.
Yes.
But we also have to take a short sugar break in the middle.
Okay.
It's 5 minutes or something. Okay, go ahead.
Okay, so hello everybody. Thanks for giving me the opportunity. So I will try to make like an introduction course on the Cuntz semigroup because yes, I know that not many people are really familiar with this subject, and usually it's very complicated and somehow abstract, and so the point is to explain you. So we'll have to, next week we have another session, so hopefully today I will end up the first two parts. So I will try to explain like the historical background, so why such an object appeared like many years ago and somehow was a bit forgotten and then reappeared like 10-15 years ago. So once I explain all of this, I will construct the Cuntz semigroup and its first properties so that you have an idea of what this object really is. And if I don't have time to finish, we'll keep on next week. And then I will show the sum of the properties that the Cuntz semigroup has. So mainly what information about a C-star algebra such an object is actually capturing. And lastly, I will present like one or two classification results related to classification of C-star algebra, right? So I guess most of you have heard about the Cuntz semigroup. Maybe you've heard that the Cuntz semigroup is more or less the Rodam Lemma semigroup, like a generalization of it. And instead of taking projection, we generalize to positive elements, which is a good way to think about the Cuntz semigroup. So if I want to go back where it all started, I have to first speak about the Rodam Lemma semigroup. Okay, so I guess most of you are familiar with this object, which basically are classes of projections in the stabilization of the algebra. And so how to compare such projection? So if I have in all the lecture, A is a C-star algebra, okay? So I have two projections. Okay. We say that P is subequivalent to Q. Basically, if there is a partial isometry that links P with a subprojection of Q, okay? Okay. What does this mean? You can see that this one is smaller. If you multiply this projection with this one, then you get back this one on both sides. Or Q minus this one is a positive element. I mean, I guess this is all right. So this is for one. And we say that two projections are equivalent. Okay. sometimes we write MVN, but since I will just use this equivalence, when I need to distinguish different type of sub-equivalence or equivalence, I will make it precise. But here it's the Murray von Neumann. So basically, if there is a partial isometry, okay, whose range is 1 and the W, oh yeah, sorry. Yeah. Okay, so one remark that we should already be saying is that if two projections are equivalent, then one is super equivalent to the other, but the converse in general is not true. Okay, so okay, but usually the converse is not true. So you take any infinite projection or but in some case, actually we have an equivalence. Okay, so this case is called usually the stably finite case. I will speak about this in a moment. But now we can define the Murray von Neumann semigroup of a C-star algebra. Basically, we take classes of projection, but we go to the stabilization. Okay. Okay. So this is the basically the completion of any matrix size, and the sum is the orthogonal sum. Okay. So we can put an addition on such classes. Okay. Okay. So which will be the class of the sum of the projection, like the orthogonal sum. So since we can go to any sizes, basically is to put the projection in block, and an order which is given by the sub-equivalence there. Okay. So what we get, so this is all well defined, and what we get is that BA is, so it's a monoid, so we have a natural element, an addition, and this is not going to be a partial order, okay? Because as I stated before, we could have two elements that compare with one another, but they are not in the same class, okay? So usually it's called pre-order monoid, and it's the pre-order is positive, okay? Any class of projection will be greater than the class of the zero projection.
Also, one question, I think, if A is stated by it, then the converse is true.
Yeah, I will come to this in a moment. So V of A is the monoid. Okay. And like you just said, so an algebra is stably finite. It means that all matrices algebra is finite, and being finite, it means that whenever we have V star V is 1, then VV star is also 1. Okay. Means that so basically every isometry in Mn of A for any A is a unitary. So if we have this, we can show that actually being subequivalent to one another implies being equivalent. Okay. Okay, so on my side, on most of the talk, I will be concerned with the stably finite case, okay, and the other case, the purely infinite case. Maybe I'll mention some. So it means that every isometry. So if you have VV star is 1, then V star V has to be 1 also. When you look at so if A is C of X, I mean in C of X usually, I mean depends on X, but I work with a nice topological space, and you have only one projection. Yeah, everything becomes trivial, and actually, I don't know much about vector bundle, but actually that's one of the reason why we need Cuntz semigroup is because in commutative setting, then all of this doesn't give you much information because you have either you have one projection, or if the X is not compact, you have 0 projection.
Like the less than squiggly thing is exactly the same as left, right? Sure.
So some remarks why this is important and why the stably finite case is important. So K0 is constructed from V of A, okay, is the Grothendieck envelope of this, and actually in the setting of von Neumann algebra, those classes of projection, they play a key role in the classification of factors, okay? And I think like the starting point was a factor is finite if and only if there exists, so what's called dimension function, which I will introduce now, and if and only if there is a finite trace, okay? In the setting of von Neumann algebra, so classes of projection play the key role together with traces which are related to what's called dimension function. Okay, so a dimension function, you can think of it as a monoid morphism from B of A to R plus. Okay, so there is a strong correlation between being stably finite and the existence of traces through those functions that are defined on classes of projection of the Rodam Lemma semigroup. Okay, but the problem is that okay, in a C-star algebra, so this was allowed from the fact that von Neumann algebra has tons of projections, and like you stated earlier, in a C-star algebra, it's usually not the case. Like we can have very few projection, or we can have, even in the simplest case, like no projection at all. I will make some example, but for example, C of X, where X is dimension 1 or finite dimension, this is stably finite. Yeah, all AF algebras, actually all AH algebra. So any inductive limits of building block of matrices over the circle or the interval is working. Like actually, it's what C-star algebra is not stably finite. It's so this you have to go more into Cuntz algebras and these kind of things. No, but there is a kind of a dichotomy in the classification. So one side was purely infinite case was classified also using Elliott invariant, and the other part is the stably finite case. If you have a trace, it's not exactly it, but if you have a trace on your C-star algebra, then it's going to be stably finite. O2 is purely infinite. I will make a, so basically what we want, like the birth of the Cuntz semigroup was to actually get something like this. Is there an equivalence between being stably finite and having a trace? Okay, so the answer is not, we cannot use no more dimension function, because in a C-star algebra, we usually don't have much projection. Okay, so for example, if you take C0 of X, okay, where X is of dimension 1, let's say, then this has no projection or one projection, which is the constant function equals to 1. Yeah. So let's take X to be the circle or the interval, okay, which are very useful C-star algebras, and you can generate tons of algebras with this. And okay, we can take this one also. Okay, so this one has a unique projection. This one also. This one doesn't have any projection. Okay, so even for the commutative setting, this thing does not give us any information on whether there is a trace or not. Okay, and actually there are. So now the idea of Cuntz was to replace projection by positive element, because we always have a ton of positive elements. Okay, because more specifically, you notice that if we have A that is a unital system algebra, okay, I think we need simplicity in this case. And A has a trace, then you can show that it's stably finite. Okay, so we have something in flavor of the von Neumann algebra. Okay, so maybe you want to normalize it or something, but then A is stably finite. Okay, so a quick sketch of the proof. So if you take an isometry, okay, so you have V star V is 1. Define Q to be 1 minus VV star, and you just apply the trace on this projection. Okay, so you have the trace of this will be so let's say it's normalized, otherwise you do it. So it's going to be 1 minus the trace of VV star, which is again 1 minus the trace of V star V, which is 0, right? And then using the simplicity, you can show that actually the trace is faithful. So you get that this projection is 0. So V star is also, so basically V is a unitary, okay? So this is always true, but how about the converse, okay? And so the idea in the original paper is to try to find an object which play the same role as this, and by study what's called dimension function, which basically is monoid morphism from classes of something. So it cannot be projection, but it has to be something bigger. Then we have equivalence between being stably finite and the existence of such functions, which in the end should be maybe not related to trace, but something what's called quasi-traces. Okay, so we will see this in chapter 3, I think, where actually this is in the original paper of Cuntz. He showed that actually the converse is almost true, but if you're a simple unital system algebra and you're stably finite, then there exists a dimension function, and each dimension function corresponds to what's called quasi-trace. Okay, so I will explain what a quasi-trace is. And if your system algebra is more exact, then quasi-traces are traces. Okay, so if you have a unital simple exact system algebra, having a trace and being stably finite is now an equivalence. Okay, so this we will see this next week. Okay. Yeah, so the trace tau. Sorry, yeah, my letters are not the best. But basically, this is what the whole thing behind the Cuntz semigroup was originally. Okay. And
was it Cuntz who came up with the idea of quasi-traces, or was this something that was known before? Like, was it in this Blackadar Handelman paper quasi traces. And I guess this was before the Kuntz thing, I guess.
I'm not sure the timeline, but yeah, they're trying to say quadrilateral, but like,
Yeah.
Yeah, maybe, but they were working with rings, no? Regular rings, or
Okay. I think they were working with the Murray von Neumann semigroup.
when I think of ultra products of CCR, I used to get like AW star algebras, which are like kind of close to one another. But like, I think that will work in the general CCR.
Yeah.
okay.
Okay. Anyway.
Yeah. So now that you know a bit of history, blah, blah, blah. Okay, let me introduce now the construction of the Kuntz semigroup. So I will not give the definition right away because actually, so this is all in 78, okay? And the way he defined this generalization of B of A in this paper is not what we actually now consider to be the Kuntz semigroup, okay? It's really close to it, but the thing is, at the time, he didn't really push to develop such an object as an invariant for classification because it was very hard to compute, and it was not continuous with respect to inductive limits. It was hard to define like the proper category which it would fall into. So I will first define all the similar things for positive elements, and then I will show why the first definition back in 78 was not the adequate, and how in 2008 they came up with a slightly different definition that is actually the right one. Okay, so first, relation on positive elements. So if I take two positive elements, we say that A, so I will write it one time and then I will forget. And actually we will see that those two subequivalence agrees when A and B are projections. Okay, so there is no conflict of notation. So A is Kuntz subequivalent to B if there exists a sequence such that A can be written as the limit of Rn B Rn star. Okay, and now we say that A is equivalent to B if they are both subequivalent to one another. Okay, so the good thing about this is that when we are going to define in a similar way our monoid, it's going to be partially ordered automatically from definition. I have to draw it, no?
I guess if you required the RNs not to be an A, but A tensor K, this would be the equivalent, I guess. So the RNs you say are actually A.
No, because I took positive element in A.
Yeah.
I don't bother with stabilization right now. I just define for a sister algebra, and we will see that actually is taking classes of positive element in the stabilization.
Yeah, sure. But okay, sure. I guess maybe I'm asking a bit of a tangential question. Like, if you, because it's a hereditary subalgebra. Maybe actually, yeah, maybe actually it does ring a bell. Okay, but anyway, maybe this is maybe it'll become clear.
No, what was the question? Because I didn't.
My question was, suppose you defined A as Cuntz smaller than B if there exists Rn's not in A, but A tends to K. A and B are still in A, but you're allowing the Rn's to possibly be in some matrix algebra.
Is it equivalent?
Is it equivalent? Because A is a hereditary subalgebra, I guess. You know, you maybe cut down by an approximate identity or something. I don't know.
You will have that if A compares with B in A tensor K, then it's the same, but the other way around. I don't know.
You can construct a W of A and then define C of A equal to W of A tensor K.
Yeah, I understand this.
But this is not related.
Yeah,
but what would be what would you gain?
This is a fair point.
Allowing those to be in A tensor K.
No, this is a fair point. I guess I'm just wondering.
Because in any case, if you want this to make sense when those are matrices, I guess you need to put B with zeros, but you need to put B in Mn of A or A tensor K.
But then A and B would still be an A.
Yeah.
They're not sub-equivalent as elements of A.
No, I don't think so. There is one implication, but the other way around. I guess you have access to more elements in A tensor K, so you could.
But I guess I was thinking you could replace Rn by something like identity Rn identity, the identity of A, or approximate unit if it's not unital. And then this would give you something that's actually in A that gives you the limit. Okay, but whatever. I'm derailing. Never mind. I think so. Yeah. Okay. Anyway. Yeah.
So to give you some example, so I don't know, is rank is called in English, the dimension of the image of a matrix?
Yeah.
Yeah, okay. Okay, so this is a spectral theorem and then you make it work out. But so this tells you actually that we will see that later on that Cu of the complex, or because it's stabilized, the Mn is just a natural number, okay, with some infinite element, but basically we can see that any matrix will be equivalent to a projection. Okay, so so X is always nice to project at space, so it's locally compact Hausdorff, connected if you want, dimension 1 or finite dimensional. So we have F equivalent to B. Okay, so this is the support, is the open set in X, such that where the function doesn't take value 0. Okay. So those are some examples and some property that are not trivial, but that are pretty useful all the time when we work with this relation. So okay, so we have
Here is tree support of Fnt divided by the sum.
yeah, it's maybe let me write it. Yes, this is pre-support. Okay. Open support. Okay, so we have, for example, okay, so this is using functional calculus. So we can always apply basically a positive element will give rise to the star home that send the identity here on A. Okay, so I mean, I think of contraction. Otherwise, you just divide by the norm of A, and the spectrum will always be included between 0 and 1, and you can show that. Okay, this defines the star home, and it's called functional calculus. Okay, so we have this, and we even have equivalence if the support, open support of A contain the spectrum. That means that it doesn't take value 0 on any engine value of A. Okay. We also have so x star is equivalent to x star x. Okay. When x in A, so any positive element of a C-star algebra can be written this way. So I will use many times this written. And also, let me mention here, for example, you can get that the power of a positive element will be Cuntz equivalent to A, okay, and can be the square root also. And is there a dry? Yeah. And a third property of this relation that I will use is that if two positive elements are close in norm, okay, then what's called a cut down of one is subequivalent to the other one. Okay, so what does this mean? So this is going to be used a lot of time, but basically it's to apply to A the function. So this is f of A, where f is this function. Okay, so to give you an idea, if I take 0, 1, so the identity represent my element A, okay? And this cut down is, so I look at T minus epsilon, okay? But since I want a positive element, so this is a star home. So if in my functional calculus, I don't take a positive function, I will not get a positive element, which is why we have to correct this and put value 0, okay? So for example, here, functional calculus is sometimes useful to picture things. For example, This guy, this cut down is obviously Cuntz below A, but it's even stronger is that we have that this is smaller than A, okay, with the order. So those things are pretty useful in everything that we're going to do today. And another thing that has been used a lot, maybe I should call lemma because it's called Rodam lemma. So this is due to Rodam, as you can guess. And it's Bayes equivalences about being superequivalent, okay? If I have two positive elements, then the following are equivalent. So A is superequivalent to B. Any cut down of A is superequivalent to B. For any cut down of A, there exists a cut down of B such that the cut down of A is Cuntz below the one of B. Okay. And okay, and the same thing here. So for any cut down of A, there is a cut down of B, such that the cut down of A can be written XX star, and X star X belongs to the hereditary subalgebra generated by the cut down of B. Okay, so actually from the definition, here you can see somehow the ideal generated by B, and what it means is that if A is called XX star, then this you can write B as square root of B times square root of B, and then when you turn it around, you get that X star X belongs to the hereditary subalgebra. Okay, so all this is a bit somewhat technical, but the hereditary subalgebra generated by the elements are really useful to picture the Cuntz superequivalence relation, and I will show that in the stable rank 1 case, which is something that is stronger than being stably finite. This is really useful, okay? And many system algebra has stable rank 1, and usually when we work, so thanks to this lemma, we can picture the Cuntz superequivalence in the following way. So let me first recall what stable rank 1 means. Unital system algebra A as stable rank 1 if, so basically the set of invertible elements is dense in A, okay? So if A is not unital, the stable rank 1 is computed in the unitization of A, okay? I also take the opportunity to recall what weak stable rank 1 means. So So supposedly A is not unital because otherwise it has immediately stable rank 1 if it has weak stable rank 1. It has weak stable rank 1. So the set of invertible element of the unitization of A is dense in A instead of the unitization of A, okay? So for now, we don't need it, but we can show later that A tensor K always satisfies this. And I need this property to get a better picture of the Cuntz relation and to show actually that any increasing sequence with respect to this thing has a supremum, okay? And this will help us to define. But right now, the weak stable rank 1, we don't need it. But in the stable rank 1 case, all of those, okay. So back to lemma. So 1, 2, 4 are also equivalent to with 5, which is there exists no. So A can be written X star, and X star X belong to the hereditary subalgebra of B. Okay, we could even take a cut down of this, but so I recall this is okay. So you can see that if A is smaller than B, then it's going to be Cuntz super-equivalent. If A belongs to the hereditary subalgebra of B, it's going to be Cuntz equivalent. So for sure, if it belongs to the ideal. And if A that I can write as XX star, then it's kind of related to the isometry there, okay? Then it's opposite, like its range, I don't know how to call it. But XX star belongs to this. Then we have that A, and it's an equivalence. A is super-equivalent to B, okay? So yeah, so that's how to picture the Cuntz super-equivalence, okay? But if we go back to projection, actually we will see that all these simplify because we get back the Rodam Lemma super-equivalence. There is something in between the Blackadar relation that it's a bit stronger than this. I think it's A can be written X, like the strongest is A can be written XX star and B can be written X star X. Okay, this is the strongest. There is another one is that, and I think it's the Blackadar one, the hereditary subalgebra of A sits inside the hereditary subalgebra of B. Okay. In the middle of this, you have the unitary equivalence. So U star A U is B, and this is the weakest because it's in the stable rank 1 case. It's actually the Cuntz super-equivalence relation. The Blackadar is stronger, that's for sure. And you're in the stable rank 1 case. The Blackadar is equivalent to this one.
So this part 5 is just for stable rank 1?
Yeah. I mean, if you have this, then you have A super-equivalent to B, and in the stable rank 1 case, the converse is true. Okay. You have also another picture of this using Hilbert modules. So there are, or open projection. There are many ways to characterize this relation. Know that in the stable rank 1 case, it's pretty nice, and know also that when we deal with projection, it's just being Rodam Lemma subequivalent, okay? Okay. Yeah.
I think they were in one if it's zero dimensional.
Yeah. C of X in one dimensional also, no? Yeah.
I guess real round zero.
Yeah. So fine. We're going to be able to find now. Why? Why? And what? Kind of an equivalence between having a trace and being stably finite. But this object have an order, and that's why
right, step right up. So I cut. All right, right here. Follow one there. Is that big enough?
Take some cards. Speaking of, now it's back. So he messaged to say there was a little blackout.
Carrot also, please. Thank you.
Chocolate. So for me, a small piece of
Small piece of both? Yeah.
I was hoping people would go for that option.
Okay, so let's start part 2, right? So now that I have this, actually, yeah. So before I give the definition, so if this is an analog to the Murray-Van der Maan semigroup, it should be, actually it's how it was first defined. So this would define actually like positively ordered monoid, because now by definition, if this is the partial order, right? If A is smaller than B and B is smaller than A, by definition, they fall into the same equality class. Okay, so okay, I will write form for positively ordered monoid. Okay. But this is not the actual definition nowadays, it's not the definition, okay? Because now we know what this object look like for several system algebra, and I intend, I don't see how much time, but to give you the first computations. But even for AF algebras, this object is really complicated. Okay, So back in the day, this was one of the first problems. Okay, it's really useful. So it solved the problem of dimension function and the existence of traces or quasi-traces in the stably finite case. But to use it as an invariant, even for so finite dimensional, it's natural number, but AF case, it's already really complicated. Okay, so it's not computable. And second point is that if you take so the inductive sequence okay. If you take this inductive sequence in C-star algebra, okay, you get that this object is not continuous. Okay, if you try to define a functor from C-star algebra into the semigroup category, for example, like naively, you get that. Okay, so if you remember in matrices, the relation was the rank. Okay, so any two matrices that have the same rank are equivalent. So that will all. So basically, we have. So this is stabilized. So this is actually not surprising, and we have the rank. So matrices of rank 1 will go to 1, rank 2 go to 2, and so on and so forth. Okay. So this inductive system. If I look at this thing, basically I get the identity on the natural number. Okay, so by the theory of abelian group, the limit of this is again the natural number. But on the other end, W of the compact operator. Okay, you can show that this is the natural number and like an infinite element. So to see this, for example, you take if you take AN to be you have the identity of MN, okay, and you take BN to be the sum of those guys, you normalize them, and you multiply them by 1/2 power 2n, so that it becomes convergence in norm, and you actually get into the compact operators. You can show that this is an increasing sequence at converging norm, and we will see that in this case, the class of B is the supremum of those guys. Okay, and basically the Cuntz class of Bn is n. Okay, and so the supremum of natural number tends to infinity. Okay, so there is a problem of completion here. So I will actually now I will talk about all of this, but the idea to get like a functor that is well defined is to first to not take m infinity of a, but to take a tensor k. Okay, so that's we can define a functor. So why this invariant regain interest? It's because so this was not introduced to be a classifying invariant, and there was this Elliott conjecture, right? So you mix the gauge theory with traces, and you supposedly it was supposed to be like an invariant for the simple nuclear separables, C-star algebra, maybe some other properties. And
And in 2003, I think, and 2005, in the 2000s, there were several counterexamples, okay? But every time the conjecture could be readjusted just by adding also with K-theory and traces, you could add maybe real rank or stable rank in order to address the issue. And in 2008, Tom's exhibit a counterexample of two-C-star algebra that agrees on everything. So traces, K-theory, like the Elliott invariant, which is the K-theory and traces, real rank, stable rank. There were stably finite, nuclear, maybe unital, separable, so they had a bunch of property. And the invariant to distinguish them was the original Kuntz semigroup, okay, the order in the Kuntz semigroup. So it said two things. The first, that the Elliott conjecture has to be, so if we want to classify those C-star algebra, we need to add at least the Kuntz semigroup within the Elliott invariant. So this is first. But since the Elliott invariant was already complicated, what Tom's really wanted to suggest is that we had to refine the Elliott conjecture. Okay, and the two C-star algebra he exhibited were not Z stable, like they were not Z stable. Okay, when you consult with Z, here appeared the differences. So on one side, they recut the Elliott conjecture, and now it's actually proven that the Elliott invariant is a complete invariant for simple unital separable nuclear blah 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 and Z stable. Okay, this regularity property was needed from the example he showed, and the Kuntz semigroup seemed to be a really nice object to classify outside the simple case or the stable case. Okay, so they wanted to use this object, but there was this problem. It's not even functorial. It's not even well defined. So in 2008, so it's Rodam Lemma and Dylan school. So they define the completion of this. Okay, so the completed Kuntz semigroup that now we call the Kuntz semigroup. And they define also in which category it falls into, so that it's continuous. Okay. Stabilization and take classes of positive elements. Okay. The sum and the order are defined likewise, and it makes this a positively ordered monoid. Okay. And they also came up with an abstract category that is a full subcategory of positively ordered monoid, in which this object falls into for C-star algebra, and for which the Kuntz functor is now continuous. Okay. So the objects are, so an abstract Kuntz semigroup is usually written C semigroup. So it's a partially ordered monoid satisfying the axioms 0104 And those axioms are, so one is that every increasing sequence has a supremum in S. Okay, so here you see that sequence that takes n to n has to fall into S, which is why this thing. Every element is the supremum of what's called a rapidly increasing sequence. I will detail what does it mean. And number 3 or 4 is compatibility axioms. Between sum and suprema, and sum and this thing that I haven't defined yet. So basically, this is called the compact containment relation or the way-below relation, and it's something that is a bit stronger than the other. Okay, it's an auxiliary relation, so it's not an order, but when you have a positively ordered monoid, if I take two elements, we say that X is way below Y, or X is compactly contained in Y, whenever I take whenever I take an increasing sequence, that has a supremum that is greater than the biggest one, then there is a finite stage that is greater than the smallest one. Okay. So usually at first this thing is a bit hard to conceptualize, so I will give you some examples. Okay, so in the natural number or natural number with infinity, I forgot to say, I will say it later.
So the question was it S and BM?
Say again?
In let X, Y, S and BM.
SMB.
POM. POM, okay. Sorry.
Ah.
Yeah, no, no.
Yeah, sorry. Positively ordered. So if you have a monoid and order, some and order are compatible, and all elements are positive.
What is S is a S is
Cuntz semigroup.
Cuntz semigroup.
semigroup. Okay.
S is and what are the morphisms of that?
Yeah, I will continue.
Okay, sorry.
I will try to make an effort with the handwriting.
So just one question, Laura. Like, so if A was separable, then I guess one you could just replace increasing sequence with an arbitrary directed set, or an arbitrary directed net. Increasing net. Is that right?
If A is not,
If A is separable, then instead of just sequences, you could deal with any arbitrary directed set.
I mean, right now I define not for algebras, I just define for.
Not for atoms. I mean, just you know a directed set, right?
Yeah.
So just like for every finite collection, you have an alphabet.
Yeah, this is gonna be true. Actually, there is this zero out DCPO thing, like complete lattices and stuff like this that you can show.
So the second case, this is a continuous.
But yeah, but what do you mean separable?
Well,
That's the same. Like right now, we talk about abstract monoids that have this property, and then when it comes to C-star algebra.
Sure. I mean, just the definition you have at the moment does not make it clear that it's actually a continuous poster, right?
Yeah, but I think this is true.
In general, or
Like you see the semigroup, it's a continuous. You can show that it's a continuous.
continuous poster,
Yeah.
like even for a non-separable, is that true?
Yeah. Because for A non-separable, this falls into the Cuntz category. So what you would have to do is to check that an abstract Cuntz semigroup is also. But this I would have to double check. But there's clearly a strong relation between these two. Outside the C-star algebra setting, just the category of abstract Cuntz semigroup is closely related to continuous poset.
Yeah. Okay.
So this is the same thing as this. In the real numbers or completion of real number. This is the same thing as this. And for example, if you take the open set of a topological space, U is compactly contained in V, if there exists K compact, such that you can put it in the middle, okay? So just to give you an idea. For example, and so for continuous function over X, F will be way below G if you can fit a compact between the two open supports, okay? Okay, I just give you the morphism. And then next week we show that CU of A falls into this category and that it's continuous and so on. So morphism are so pomorphism. So basically it's a semigroup morphism that respect the order, and they have to respect the way below relation or the compact containment relation and the suprema of increasing sequence. Okay. So basically the thing that makes everything work is that we can prove that every increasing sequence has a suprema. Okay, this is the hard fact of showing that CU of A falls into this category. Okay, and then how and why they define it this way is to make the functor continuous, but how they come up with those abstract axioms, I guess they're really smart. And so the point is, I'll show you not the full proof, but they showed it using, so there is another picture. Instead of using positive element and hereditary subalgebras, you can use Hilbert modules, okay? So the superequivalence is easier to describe than, at least for me, the objects are harder to picture. And so they show the existence of suprema using the Hilbert module picture, and I will show you, like, not the full proof, but the sketch of the proof on how to have the existence of suprema using these kind of pictures. Okay, and then we will go to part 3 and 4. So we will see that the Cuntz semigroup captures really well the ideals and the quotient of a C-star algebra. There is, so you could define, but also exact sequences, and the Elliott invariant captures the Elliott invariant in the simple case, simple set stable case. And I will finish with some use of this invariant for classifying C-star algebra. Okay, so basically this is a program from next week. Any question?
One question. So I was wondering with the weight below relation you just defined there, in a particular case, you have a semigroup coming from a C-star algebra.
Yeah.
Is there maybe a sort of more C-star algebraic characterization of the weight below relation?
Yeah, somehow. So, for example, I didn't say, but if X is compactly contained in itself, it's called compact element. Okay, and you see in the stably finite case that those are exactly classes of projection. Okay, so this is the first characterization of compact element, and then you can show that any cut down is what I defined earlier is way below the element. Okay, and basically this O2 thing, usually when you have to approach an element using not an increasing sequence but a rapidly increasing sequence, you just take the cut downs and the epsilon is 1/n. Okay, so this is really useful. So basically an element you can approach it like by cut downs in such a way.
Okay, so if I understand correctly, to say that A is way below B is equivalent to saying there exists some small epsilon by which you can cut down and still A will be Cuntz.
Exactly.
So, yeah, okay. Thanks.
Great, so Laurent answered Zoom way, I guess. So we won't hold you to questions.
And
You have to remember your questions for next time.
yeah.